So now we're going to take a look at limits and continuity with several variables. This will be similar to domain and range. We're not changing the rules here of the game, but we are building upon them with more than one variable. So if I'm looking at limits and continuity, first let's compare the behavior of these two functions, and let's look at what happens as y and x both approach 0. So therefore meaning I'm approaching the origin, because if x and y are 0 in the three-dimensional plane, that's getting close to the origin, just like it would be in the two-dimensional plane. So if you remember with limits in your basic single variable course, we could use the table function of our graphing calculator. So what I've done is I've just kind of created a table function to see what happens to this behavior as x and y trend to 0, which would be right here. So as I'm trending to 0, I should notice that 0 and 0 don't align because my function is not defined at 0, because 0 plus 0 is going to be undefined. So I know it's undefined here, but if I look at what's happening as this approaches 0 and as this approaches 0, it appears to be approaching 1 from both sides. That's important. Now if I take up my second function, my g function, here I am at 0. And if I look at what happens as x approaches 0, it goes to -1, and y approaches 0, it goes to -1. So what you would do to create this table is you would be looking at x values of -1, -0.5, -0.2, and then I've got 0, 0.2, 0.5, 1.0. So you're just constructing a table just like you would in single variable calculus. So based on that evaluation, it does appear that xy approaches 0 for the first function, as x and y approach 0, the values are approaching 1, whereas the values of g of xy aren't approaching any specific number. So if I just look at this row, it looks like it's approaching -1, like we said. But what happens when you exclude from this row? Well, if I'm at -0.2, it's at 0, and it's at 0 here. That's a little bit questionable. Let's look at the first one. Here, do you see how these numbers match up? So no matter which way I come at it, I'm going to 1. I'm going to 0.9. I'm going to 0.9. Here, I don't have that behavior. It goes from 0 and jumps to -1. Same thing here. It goes from 0 and it jumps to -1. So if I'm looking at this table, even though this row appears to approach -1, you have to take in the big picture of all the numbers. So if I'm looking at all the numbers, I see this weird phenomena from here to here. I can't make a jump that's a whole number step. And that means that that secondary one, that limit does not exist there. So in general, the way we use notation is instead of saying the limit as x approaches a number, we say the limit as x comma y approaches a number is L. Just like we saw before with limits, it has to approach the same thing from both sides. So if in order for there to be a limit, it has to approach the same thing from both sides of the function. This is just the definition of a limit. You don't need to worry about the definition of a limit with error. We're not going to get that far into limits, but I did want to just kind of show what it looks like so you're not totally thrown if you see it. Another notation that I personally don't care for is the limit as x approaches a and y approaches b. Just because it's really hard to type that and it gets super tiny. So I don't tend to use this often, but occasionally there are textbooks that will use this. And then this just says we've got to make sure it approaches the same thing from the right and the left. Otherwise, the limit doesn't exist, just like we've been doing in all of calculus. If you have forgotten the limit rules, go to my YouTube channel and look up limits, and you'll find quite a large series of lectures on limits that you can watch to refresh yourself. So for function of two variables, it's not as simple as just looking at the y value like a single limit, just like we saw in this table. If I was just looking for that one value, I would just be looking at this row. But I have to look holistically at what's happening, otherwise I could miss something. So my definitions say that I have to make arbitrarily or sufficiently small steps to get to my limit. So I can't jump from -1 to 0. That's not going to be small enough of a step to say that it's approaching something. It's another way of looking at the distance between points that are occurring between x and y and a and b. Notice that the definition itself doesn't refer to the direction of approach, so I have to know that it has to approach the same thing from both sides. And if the limit exists, it must approach the same limit no matter how x and y approach a and b. So my actual function, so again, if I look at that table, x and y are approaching 0 the same way, but it doesn't matter. What matters is what's inside the table, and that's what that's telling us right there. So if I find that there are two different paths and it has two different limits, then it doesn't exist. So if one side's approaching 5 and the other side's approaching 4, the limit does not exist. So what does an example look like? Well, let's look at this. Let's show that the limit here does not exist. Well, the first thing I'm going to do is plug in 0, 0. When I plug in 0, 0, I get 0 over 0, which is not 0. That's an indeterminate form. So then I need to look at, okay, I need to do something else besides just plug in. So I say, well, let's see what happens as I just have one thing approach 0. So if x approaches 0, and I zero out my x values, I get negative y squared over positive y squared, which is negative 1. If I look at as y approaches 0, then I get x squared over x squared, which is positive 1. So because they're approaching two different things, the limit does not exist. So I would say that this is what, sorry, and let me just clarify, this goes with this statement. So it approaches 1 as x and y approach 0. But when x equals 0, I'm getting negative 1. And because they don't match, the limit does not exist. So this is the rest of that pointing out that if I zero out the other one, I get negative 1, so then my limit does not exist. And this is just kind of an image of negative 1, positive 1. They're not going the same direction, so then the limit definitely does not exist. So now let's look at a limit that does exist. And so if a limit does exist, it's going to match from the right and the left. And I need them all to match up in this case. And the squeeze theorem still holds true as well. So if I change this problem up here to x squared plus y squared, it would have a limit that existed, and that limit would be 1 because no matter what I do with reducing x or y, I'm going to get 1. So that's an easier case. The cases where they do not exist are a little bit tougher to work with than looking at when they do exist. And so make sure you're looking at the x value and the y value separately as you do limits. Now, what does continuity look like? These graphs are a little bit crazy, right? The graphs are hard to visualize. And so continuity means that if I evaluate a limit of a continuous function, then that's always easy. Continuous functions always have a limit. It can be accomplished by just plugging in. So I can just plug in my 0, done. Continuous functions of two variables also allow you to direct substitute. So I could not direct substitute in this problem because I got 0 over 0. If you don't get an indeterminate form, you can just plug the numbers in and what you get out is your answer. So when I'm talking about continuity, it means that there's no hole or break, which is different in 3 dimensions than 2. So I can't use the rule of thumb that when you pick your pencil up, that means that you don't have a continuous function. That's not going to be something I can work with. If I have a polynomial of 2 variables, then let's say I've got x to the m, y to the m, where c is a constant value and m and n are non-negative integers. So I've got, those are all going to be numbers. Then the rational function is a ratio of polynomials. So if I've got m and n, then I have a polynomial, for instance. So I can look at f of x equals x fourths to the 5xy squared, 6xy to the fourth minus 7y plus 6. That's a polynomial. That's going to have that limit I can just plug in to find. But if I look at g of x, that's a rational function. that's going to potentially have, I'm not going to be able to do that because I might get 0 over 0. Now, in this case, it's x squared plus y squared, so I'm only going to get 0 at x and y is 0, so that's going to be a problem. But if it was this one, I could plug in 0, and my limit would be 6. So here, I've got a different problem happening. How does continuity affect things? Well, let's take a look and see let's see what this one does. 2xy plus 1 over x squared plus y squared. Let's try it out. And again, this is very handy for those of you who are visual. 2xy plus 1. Ooh, look at that. I have a lot going on right there. So the purple area would be what this function actually looks like. For some reason, it's not letting me back out that other equation, so we're just going to keep going. And so if I look at this, what's happening right here is it looks like I have a discontinuity, possibly. So I would want to investigate that a little bit further with a rational function to see if there is a discontinuity or not once I graph it. It's not nice and solid like the ellipsoid was, so that's kind of something that I would want to investigate a little bit more. So to be able to do this, I've got to think about limits in terms of the regular coordinate plane. And the regular coordinate plane, I know that if I've got it equaling to numbers and the limit exists, then it's possibly continuous. I say possibly because asymptotes can have a variable and so can a whole, can have a limit that is evaluatable. If it's a polynomial, then that's nice because they're always continuous. And likewise, rational functions are continuous on its domain because it's a quotient of two continuous functions. So that answers this question. This is a rational function, so the fact that it has this hole in the graph is not the same as having a hole in a two-dimensional graph. It's very different. So that is considered continuous because it's going to keep getting taller forever. So here's another example. This is a polynomial, which means it is continuous everywhere. And if I want to find the limit of a polynomial, it's continuous everywhere, so I can just plug in 1 and 2. So I just substituted 1 and 2, and I got my limit is 11. I don't need to make a table. I don't need to graph it because it's a polynomial, and I know it's continuous everywhere. So continuity is going to play a heavy role with looking at, is it going to have a limit that exists? So how does it work with 3 or more variables? Well, it works the exact same, but I have a z. So I can still plug in directly. I can still, I don't need to do that one. I can still plug in directly. I can still do other things. So this right here is a rational function, which means it's a ratio of continuous functions. So I could just plug the numbers in. So this is what the definition looks like of a limit. Again, we're not stressing over this, just so we can see it. But whether you have 2 variables or 3 variables, all polynomials are continuous. All rational functions are continuous, which is different when I'm talking about y equals 1 over x. That's not continuous. But when I have 2 or more variables, that thinking does apply, and you can just substitute. It's going to be times where I have a rational function like 2 minus x squared minus y. That's where I'm going to have to plug in to get the table like we did at the start of the lecture.